This is the part 2 of module 5, that is voltage source inverter fed induction motor drives. In the previous lecture, we discussed the basic concepts of VSI fed drives and two different configurations that are the PWM inverter drive and stepped wave inverter drive. Today we will discuss the methods of braking of VSI fed induction motor drives. That is how dynamic braking and regenerative braking are implemented in a VSI fed drive. Braking and multi-quadrant operation of VSI fed induction motor drives. First of all, we will discuss how the operation of a VSI fed motor drive shifts its operation from motoring to braking. This was already discussed in the lectures of module 4. The power that is fed into the motor, that is the stator of the induction motor, is equal to Pin equal to V 3 VIS cos phi, where V is the fundamental component of the motor phase current, that is the stator input voltage, fundamental component of the stator input voltage. IS is the fundamental component of stator current. All these are per phase values, and phi is the angle between V and IS. So we have to keep in mind that Pin will be positive if machine operates in motoring mode, and Pn will be negative if it is in braking mode. So for the power Pin to be positive, the value of cos phi should be positive. That is, the value of phi should be less than 90 degree during motoring, and we have to make it greater than 90 degree if we have to shift the operation to braking. The same concept is discussed here. In motoring operation, phi is less than 90 degree, therefore Pn is positive, that is power flows from inverter to machine. Now how it operates in braking, that is second quadrant, how it shifts from motoring to braking. When frequency is reduced, the synchronous speed becomes less than rotor speed. That is, synchronous speed is equal to 120 f by p. So if f is reduced, synchronous speed is reduced. But due to inertia of the rotor speed is not affected at that instant. So what happens when frequency is reduced? That is, synchronous speed is reduced. Then the value of slip, or value of the relative speed between the rotor conductors and rotating magnetic field, will reverse, or it becomes negative. During motoring, the relative speed was positive, that is omega s minus omega m. During when the frequency is reduced, then the value of relative speed, that is omega s minus omega m, becomes negative, since synchronous speed becomes less than rotor speed. So since the relative speed becomes negative, the EMF induced in the rotor, that is the rotor induced EMF, which opposes the relative speed, or which tries to nullify the relative speed, the amount or the value of that rotor induced EMF reverses. So this reverses the rotor induced EMF, obviously rotor current, and the component of stator current which balances the rotor current. All these values will reverse. So we have to keep in mind that the component of stator current which balances the rotor current, rotor ampere turns, also reverses. That means a component of IS will reverse, or it will become negative. So obviously, if during motoring the angle between V and IS is phi, that is less than 90. If it was less than 90 during motoring, then when a component of IS becomes negative, that means uh, 180-degree change happens for that component of IS. That means IS will shift. The angle becomes greater than 90. Angle between V and IS becomes greater than 90, leading to uh, um, braking operation. That is P in becomes negative. So consequently, the angle phi becomes greater than 90-degree and power flow reverses. That is, power flows from the machine to the inverter. The machine works as a generator feeding power into the inverter, which in turn feeds the power into DC link by reversing the DC link current ID. And there are two possibilities. Either we can use or usefully do some work with the help of this regenerated power, or we can just waste that power in some resistance. So if we are usefully employing that power somewhere, it is known as regenerative braking, and if we are wasting that power in some resistance, it is known as dynamic braking. Now let's see how regenerative braking and dynamic braking are practically implemented. So this is the circuit diagram used for dynamic braking in a PWM inverter fed induction motor drive. This circuit diagram is familiar to us, that we have already seen this circuit in the previous lecture, but the only difference is that we have incorporated dynamic braking in this circuit. That is, we have added a switch SW and a self-commutated switch, that is transistor, and a series resistance, braking resistance. These are the additional uh, components or additional elements that are added for dynamic braking. Otherwise, this is a simple VSI fed induction motor drive using PWM inverter. We had already seen this circuit in the previous lecture. So let's see how this helps to implement dynamic braking. So in this circuit, ID is the DC link current, which is positive during motoring and negative during braking. First, when the operation of the motor is shifted from motoring to braking, then the switch SW is opened. That means the power flows from machine to inverter in this direction, in the negative direction. So the power flow should not be allowed to the source. Since there is a diode bridge, the current will not be allowed to flow in the negative direction. Anyways, we will open the switch SW. So at the same time, the generated energy flowing into the DC link charges the capacitor and its voltage rises. That means when the switch SW is opened, then the circuit consists of the PWM inverter, the resistance and the switch, and the capacitance. The rest of the portion will be disconnected or eliminated from the circuit. So when the motoring operation is shifted to braking, then power flows in the negative direction, and the energy generated by the induction motor during braking will be used to charge the capacitance. Since the current flowing in the negative direction, the capacitor will be charged, but the capacitor voltage will be continuously monitored. When the capacitor voltage crosses this set value, a predefined value, then the switch S will be closed. When switch S is closed, then the current will flow through the resistance and through the switch. That means the energy generated will be dissipated in the resistance. The energy generated in the machine during braking is dissipated in the resistance R since S is closed. So at the same time, the capacitor C, the energy stored in the capacitor C is also dissipated in resistor R. But only a part of the stored energy will be dissipated in R. During this operation, the value of VD, that is the DC link voltage, reduces. We are continuously monitoring the voltage across the capacitor, that is equal to the DC link voltage. When it becomes equal to a nominal value, or it becomes equal to a set value, then the switch S is opened. Again, when the value of C becomes equal to a preset value, then switch S is again closed. So by closing and opening the switch based on the value of DC link voltage, generated energy is dissipated in the resistance, giving dynamic braking. The only disadvantage of this method is that the generated energy is wasted in the resistance R without using it for driving any other load or any other purpose. But it is a very simple method of braking of VSI fed induction motor. Next is regenerative braking. Let's consider these two circuits. In the first circuit, the power supply is a fixed DC supply which is connected to a PWM inverter to feed the induction motor. So during motoring, the current is positive, and during braking, then the current flows in the negative direction, and the current will be fed to the DC supply, providing a negative flow of current. The power flow becomes negative. So this DC supply is an inherent property or capability for regenerative braking. This supply allows regenerative braking. So if we have a DC supply, then there is no additional circuitry required for implementing regenerative braking. Regenerative braking will happen by its own. But if we have an AC supply, three-phase AC supply, then we have to rectify this using a diode bridge, and it is to be given to a PWM inverter. These two circuits were discussed in the previous lecture. So if we have an AC supply, there will be a diode bridge. So the specialty of diode bridge is that it will not allow flow of current in the negative direction. So during motoring, current flows in this direction, that is motoring, and during braking, current will not be allowed to flow in the negative direction due to the presence of diode bridge. So instead of using diode bridge, we have to use some other circuitry which allows flow of current in both the directions. So either we have to use, or we can use a dual converter which allows current in both the directions. Dual converters were used for this purpose in the earlier drives, but it consists of a large number of switching devices, which makes it very much complex to control that drive. So dual converters are not used nowadays. Instead of dual converters, we can use synchronous link converter, that is SLC, which has a very superior characteristics or features for providing regenerative braking, in which there is an AC input power supply. So we will discuss the synchronous link converter and its operation in the next lecture. Thank you.